Today, I'm just going to give an overview of what is happening about this deep low-frequency radio observations, particularly using uGMRT. As you may know, uGMRT is a SK pathfinder for India, and we have been using it quite a lot within the group and within this consortium. So SK India is a... Can you hear me?
Yes, we can. Yes.
Yeah, okay. There was a feedback. Okay, thanks. So SK India is a consortium of several institutes. And within that, we have a science working group, quite mimicking the working group of the International SK Forum for cosmology, which includes cosmology in radio frequency bands, which relates to epoch of reionization and cosmic dawn. So this has been an effort primarily from my group, as well as collaborating with a lot of people within the collaboration using Nirupam Roy from IISc and others. So we'll proceed forward. Just to give you a hint, what is this all fuss about? We are talking about cosmology. So this is a picture of the since Big Bang. As the universe expanded, it cooled, it recombined, and it remained neutral over this entire dark age period where there was nothing to light it up. You have to wait till the first stars, first galaxies, and black holes came up. And that is the epoch which astronomers and cosmologists says cosmic dawn, mentioned as CD over here. And as the universe, as these structures grew, the universe became more reionized. A neutral fraction jumped from 1 to the power -3. So that's the period where we say the epoch of reionization, which it peaked, and then finally it went down to the neutral fraction, which we see today. So because of the Lyman alpha is typically used to probe this kind of IGM large-scale structures at the lower frequency redshifts, but it becomes completely non-usable at this redshifts for the high neutral fraction. So the usual probe is H1 21 centimeter line, and for this redshift, it comes down to a frequency below 200 megahertz. And that's why there hasn't been much progress in this for till last decade, when new telescopes came up, LOFAR, primarily MWA. But also there has been significant efforts using GMRT. There was a full UR program using GMRT. There has been certain upper limits, which will come soon. But primarily, you see the major players, telescopes in this realm are LOFAR, MWA, HERA. Paper was there, which is transformed into HERA. And then, of course, the upcoming SK1 low, which India is a part of. So for this talk, we primarily concentrate on, so this SK1 low is this particular portion of the sky of the redshift, which covers the cosmic dawn and epoch of reionization. I will mention the uGMRT efforts, which basically started from the post-EOR regime at band 3, which goes from 300 to 500 megahertz. But also we have started probing down into 150 megahertz band 2. And we have some initial results, which we can share, which is encouraging. And of course, I will advertise something which we are trying to do from the space, which will cover this part of the dark age. So just a broad overview of the telescopes which are currently working. Of course, GMRT had a lot of experimental results before. Mainly, the PI was Wellipen from CETA, Toronto. And they have put some very useful upper limits when there was nothing else in the literature. But then soon it was taken over by LOFAR paper, and then LOFAR and MWA, which has lots of results. And the HERA also started producing useful upper limits, which will constrain a certain parameter regime of this in the redshifts. This is a summary of the all the upper limits still today. Sorry. It is from a HERA collaboration paper in 2021. So not that far away, and nothing has been produced since then. So people are crunching data, and we can tell what are the complexities and why it is not easy to just put up a new constraint every other day. It's a whole list of things, but you can see this is this broad solid line bottom at the expected signal level, and we are pretty much about order of 2 magnitude higher in this space, which is delta square in its power spectrum dimensions in millikelvin square. We'll come into that later on. But nevertheless, we just remember that we are still order of magnitude 2 off from the expected signal range. Of course, the context for this talk is for this upcoming telescope, which I think by this time you all know that the SKA will be in 2 parts, in Western Australia, which is the right-hand side. It is an aperture array kind of a telescope. Each tiles kind of mimic each telescope, one dish, which is shown in the left-hand side, which is SK1 mid. And so while the designing and the final configuration studies are getting finalized in Western Australia, a lot of efforts have already started. And I think I saw in the program, Philippa is going to talk after this. So she may also fill up with that. Primarily, initial work has started in Western Australia to put in 1 or 2 tiles and to study what is the effect of that in the bandpass, band shape, and so on. So there have been a couple of results which are a little bit warning. So people have gone back to the board and tried to understand how to repack the elements, all these dipoles in a better manner so that it doesn't give a ripple where we want to see the signal at. This is a sensitivity curve showing all the future telescopes, SK1 mid and SK1 low, but also there's uGMRT, and we don't have the NGVLA curve here. But if you look at this curve, till we get SK1 low, which is probably 8 years down the line, optimistically, I think uGMRT is still a fantastic instrument covering this particular band, going from band 4 end to band 2. If you are using if you are a uGMRT user, or to translate to frequency, it basically going down from say 600 megahertz down to about 150 megahertz. It will still be the best telescopes given the resolution. Okay, so use it well. That's pretty much my pitch. A lot of proposals comes. So what is the problem with this, with doing this kind of a precision cosmological experiments with from the ground? No matter from where you do, one thing you cannot, you cannot get rid of is the foreground. So the signal, which is of the order of 10 millikelvins, say, is really crowded over by the foregrounds, which are extragalactic, galactic foregrounds. The signal for everybody else is basically noise for us. So unless you remove this signal, this noise, this huge bright foregrounds, up to certain order of magnitude accuracy, we cannot be detecting the signals, because any subtraction of these foregrounds will create or mimic some residual signals which will offset our actual knowledge of the signal. So care has to be taken in the foreground subtraction, much like the CMB people. But we have our own challenges at low frequency. We'll come to that. But to take home message is that the foreground is 3 to 4 orders of magnitude or even higher than the signal itself. And this has to be removed from the data set to the huge amount of accuracy to get to the signal. That's the challenge. So here we have a curve which shows in the angular power spectrum domain, which is our signal. And this is where your galactic synchrotron lies over here, galactic free emission. And so many orders of magnitude higher is the CMB. And so that's the challenge to remove it. we have in the foreground, we have the diffuse emission from our galaxy itself, the synchrotron radiation, which is diffuse. So again, it becomes much harder to remove than the point sources, which are extragalactic. This is a slide from our own TGSS survey with the GMRT done by Samir, who has extracted all the information, angular power spectrum of the synchrotron emission from the TGSS using tapered graded estimator, a method which is well known and used in our group and collaboration. That is galactic foreground. Coming to extragalactic foreground, this is the typical field actually from our observations of the LIS-01, a very well-studied radio deep field. And you can see there are lots of point sources, lots of extended sources, which covers the entire scene. So you have to remove every one of them, and with defined calibration accuracy and positional accuracy, so that it doesn't have any remaining residual foregrounds in the data set which can obscure the signal detection. You can already see, if you can see, I do not know, there are these ripples which makes a point source looks like an extended one. These are typically a feature of calibration not being done well, or there is some residual calibration errors, which can be because of something we missed in the data set, can be RFI, can be some baselines which have not behaving well, some antennas gone bad, which we haven't been able to remove it with correct accuracy, or there is our own atmosphere, the ionosphere itself, which creates kind of this white field effect, which kind of grows from the field center to the outside periphery in the beam, the primary beam, or the field of view. One way to quantify these extragalactic foregrounds is doing this CDF cumulative distribution curve, called log n log s or DNDS in this. And there are a lot of studies at different frequencies, mostly in L band or 1.4 gigahertz, because there we have the most sensitive telescopes like the VLA, which has done the most all-sky surveys. Right now, also 5 gigahertz survey is being done. Below that, not much of all-sky survey have been done except TGSS, but that is limited to some sensitivity. Of course, VLA has done a 4-band survey, or the VLSS, a 74 megahertz survey, but that is also very sensitivity limited. So the problem is that our foreground knowledge is sensitivity limited, but that's what creates the systematic error for the signal detection in our case, because the experiment which we are on to detecting this faint signal, that is actually not sensitivity limited. You can observe for nights and nights, and you should be able to get down to the particular signal level which we want to reach. However, you have to still remove the foregrounds to that accuracy. But foregrounds are limited because of the existing surveys. It is limited to some amount of accuracy, and that cannot be removed from the data set which is observed for the cosmology, just impromptu. So what it means is that we don't have independent observational data sets of the foregrounds up to this accuracy, which we can use to remove from our data sets and get to the signal, cosmological signal ad hoc. What we have to do is that we have to use our observation to constrain both the foregrounds and the signal at the same time. And that increases the challenge of these particular observations humongously. Okay, so that's how to do that. There is still some, I should not be only giving negative news, but there are lots of positivities which will come to the end, towards the end of the talk. Going deep, I think there are several challenges, like apart from what we have discussed, the foregrounds, there are instrumental effects. That the beam, our primary beam is chromatic, and we have to use that wisely. Most of the primary beam information are also limited, particularly, at least for GMRT, it's a dish. So we know the primary beam up to some certain level of accuracy, But for the aperture array, again, the beam information is limited. Ionosphere, I've already mentioned. Then apart from that, the calibration error, the polarization leakages are also creating more trouble to go on. I skip this and go on. Yeah, and there are several others, like, okay, if you have two different antennas placed side by side, there can be mutual coupling between them. That also has been detected in, in experiments like HERA. There can be cable reflections. If your cable is long enough and you haven't properly calibrated things, then the cable reflections can show up in your final power spectrum, which you want to detect. So those all have been detected and quantified by these Pathfinder experiments and HERA. So this is a good sign, because when finally things starts off with SKA, we have certain understanding what are we going to face. So yeah, apart from that, there's a huge data set. So tons of data are going to come, because you want to record the data at the highest possible time sampling and frequency sampling to be able to deal with the RFI, the radio frequency interference, and other effects like the ionospheric and other things. So how to deal with that? So RFI, we all know, if you're a radio astronomer, RFI has been a pain since the beginning, and it's all through, particularly for GMRT, there are a lot of broadband RFI sources, which has been a problem from our experiences of band 3. And we have been almost, excluding 40% of the data. For band 2, we are almost excluding 60% of the data for RFI. So better RFI excision algorithms to do it at more higher time and frequency resolution will be, that will really help. So a lot of people are working on that. So our efforts, I just summarize before I show those results. So we have started observing at band 3, because when we started off in early 2017, we didn't, the band 2 was not quite ready. So we started off with band 3, which is more well-behaved, although very well knowing that this will be in the post-EOR regime. And then recently, last 1 or 2 years, we have started reducing some band 2 data, observing, understanding what that means. And I will show you some exciting results from there. But also parallelly, the group has been studying how to simulate each of these systematic effects to understand their effects results in the final data set. Because when you get a real data, actual observed data, you have everything mixed up. So to understand individual contributions is very much requirement to develop an end-to-end pipeline to simulate each of those errors so that you can try to constrain them and deal with that. And for the extraction, for the extraction of the signal, we use machine learning techniques, which will not be showing in this particular talk. But if you want to chat, we can chat offline. This was our first result from uGMRT band 3, which is 300 to 500 megahertz, done as a part of the thesis of one of my first few PhD students, Arnab, who is now a postdoc in McGill. This was kind of the deepest image at the band 3 for a long time. Maybe it's still that. 15 microjansky per beam is the noise, RMS noise, which we reached, be able to attain out of I think 26 hours total observing time, given I think about 18, 19 hours on source time. So this is still direction independent image, because we haven't been able to apply direction dependent calibration on this particular slide. So that was the first result. There is some exciting, source studies. We have done a lot of this angular power spectrum to understand the synchrotron radiation. We have constrained them using tapered gridded estimator, which I showed earlier, Samit Chaudhary's work, who is now in IIT Madras. One of the interesting and confusing results from this particular work was that when we look at this angular power spectrum across this wide band of uGMRT from 300 to 500 megahertz, we see a break somewhere in this angular power spectrum near frequency of 400 megahertz. This is still, we have not investigated further. We wanted to, but we didn't get much time on the GMRT to do this. we will keep trying to get time. One of the reasons it's hard because uGMRT is an open telescope, and we have to fight with everybody to get some time. So we will improve our proposal and try to see if we can get time to confirm this result, which will be interesting. We have done source study. Another PG students, Akriti Sinha, about to finish. She has done a lot of individual source study, understanding the classifications, what is the different star-forming galaxy versus AGNs, and a lot of other results have been worked. This paper is mentioned here. Moving on to, so that was the band 3 result, which was mostly post-EOR because we are not quite into the EOR regime, which typically redshift 8 is basically 150 megahertz. Okay, so we got some initial time on uGMRT, 8 hours to begin with, and then further 24 hours on LS-01. And initial results were not that conducive to proceed with further study. But then we kept on improving our analysis and looking into chunks, did massive RFI excision to finally able to reach to a initial image, first of its kind. We have received, we have able to go down to 240 microjansky per beam out of 24 hours of observing time. It looks quite glamorous, given that this is band 2 image from uGMRT. 190 megahertz kind of. Okay, so it's still, you can see this sources which looks like these stars with the spikes coming out of it. They are improper calibration, majorly due to ionospheric effects. They are very strong sources, so these things build up around the strongest sources. But either in the side you can see diffuse emission and a lot of this interesting giant radio galaxies showing up at the edge also. So we are finalizing this, and it will come up soon and will be submitted. So stay tuned. If you look at the individual sources, there are very exciting radio galaxies in the field, and they can. Okay, I will wrap it up. So this is the going from 190 megahertz, how it goes to 1.4 gigahertz. We have shown these images. We'll skip that. We have developed, we have used TGE, and we are now using also image-based angular power spectrum estimator and trying to compare both methods to understand what it does. We're not only limited to LS-01, but we're also looking into other radio deep fields like Bootes. This is one of the band 3 data. Some archival data which was left over, nobody analyzed it, so we started doing that. This is also Akriti's thesis. Yeah, and okay, so coming to so what we do after we observe, our primary work is after the foreground subtraction has happened, we convert this image cube into Fourier space in doing a Fourier transform in all 3 directions, 2 angular directions and 1 frequency direction, because it is a redshifted signal, so frequency direction also is the line of sight axis for us. So if you do that, you convert into this cumbersome power spectrum domain, and we have done that. One of the problem in doing this third axis Fourier transform is, if you have done RFI excision, there will be missing channels. Moment you try to Fourier invert that data along that direction, you will create spikes. It's very well-known fact. Anybody used Fourier transform knows. So we have to do something to get out of this. Okay, there are methods to do that. So one of the last of Arnav's thesis work was regarding that. So we have used this one-dimensional clean. Clean is a very well-known algorithm which all radio astronomers use in 2D to create a clean image. But here we are using it to create, to make use of the missing channels in the frequency domain. Okay. And another method is this LSSA, which is basically a linear least square fit to interpolate that missing channel. We have done the comparison. We have found that LSSA is working better in different RFI scheme than the clean, and that has been published also as a paper in ABJ. our initial upper limits from this band 3 work have been published, and we are around the ballpark like anybody else in the post-UR regime. But we definitely are gearing up to analyze and come up with the results from the band 2, which will be coming up soon. As the image has been finalized, the initial paper will be submitted by, this is a thesis of Rashmi Sagar, one of the new PhD students of mine, and stay tuned for these results for the upper limit on the, now it will be the EOR regime. So we are all excited about that. A little bit of glimpse, but last 2 minutes on this. Synthetic observations, as I mentioned, are very important. So we have created this end-to-end pipeline.
2 minutes, could you wind it up?
Yes, that's 2 minutes is fine. Thanks. So this end-to-end pipeline, basically it creates, given any array configuration, mostly we will be using SK1, but we are also using HERA and other MWA configurations, and you can create simulated visibilities. You can corrupt it with any known calibration terms you have in mind, RFI, and then you can convert them to image and power spectrum. You can do your validate your signal extraction pipelines using this particular method. That was a primary building block of one of another student's thesis, Ashila Mazumdar, who is now a postdoc in Manchester. After we do that, the idea is for our group, we are following the ML techniques. We use neural networks, deep learning methods to basically extract the signal in presence of the foregrounds. Okay, this is a rough sketch of what we do. But this is beyond the scope of this talk, so we will skip that. That's what we have progressed. However, if you go further, this is what we spoke about the cosmic dawn. So you can barely go down till 80 megahertz in the frequency with the, that is on the surface of the Earth. If you go further down, you're approaching the dark ages, actually higher than 36, so below 30 megahertz frequency. It's difficult, almost impossible to do it from the ground because of the ionosphere. So there are several missions which are planned, Farsight, Dapper, my collaborations in US. There is a lot of Netherlands, China collaboration is going on. Some things have been already landed on the surface of the moon, but the results are awaited. Pratyush is one more thing from India, which is planned, mostly in this cosmic dawn regime. And one I'm involved in is called SIMS, which is working below 30 megahertz in the frequency range, and looking at galactic spectrum at these frequencies, but also the cosmological signal. So this is just a glimpse of the SIMS payload, which has been shortlisted, and we have to propose and go to the project mode with ISRO. So before we finish, this is the summary. uGMRT is a fantastic instrument at band 3. Band 2, as I showed the results, it's not untouchable. It can be made use of. Little bit lucky because you have to look into the sources which are a little bit higher in declination. Moment you look something which is very low in declination, you're actually looking through the higher amount of ionosphere, as well as most likely you will be intercepted by a lot of RFI. That also we have encountered with another particular field, which is slightly southern. End-to-end pipeline is being developed by your group, and that will feed into the data challenge efforts from SK, which other talks have already been covering. So I stop there. Thanks for your attention. Questions if you have. Thanks.
Yes, thanks for really a lot of great work. Just because of the time, we will just have one question. Surajit?
Hi, Surajit.
Hi.
So you told that removal of foreground is a complicated job and all. So I was just wondering, you have some for some of the region you have very deep observations, right? I mean, liquid field cleaning and such kind of thing. So whether those can be taken as template and do some Monte Carlo simulations to generate a all sky and then remove it, is it possible? Something kind of that.
Yeah, I mean, definitely. I mean, foregrounds are assumed to be spectrally smooth. So basically, you can assume some spectral index, and you can. That's all we have been using so far as a prior, good prior. But again, I mean, you have to understand that we don't really have the information from if you have to remove a data set, foregrounds from a data set which is 1,000 hours of observation, typically your observed foreground should also be from that same data set to begin with. But yes, I mean, in the parametric, non-parametric techniques of removal, we can definitely use prior information of the foregrounds from the higher frequencies and bring them down to lower frequency following some scaling rules. And we can do that. Yeah, typically that's what we have been doing. But there are some limitations to that, and that we have to understand.
Yeah, thank you. Yeah, thanks. We thank all the speakers of this question.
Long live India and France friendship.